Welcome back to Algebra with Miss Swartz. Today we're continuing on with our linear functions discussion. We're going to be looking at a few different pieces with the linear functions and just some examples of some graphing and those types of things. So I'm going to be using the idea, okay, we know what a linear function now is. It has to be in the form of y equals mx plus b. And we know it has to have a constant rate of change. So now can we kind of apply that and can we see that on a graph? So let's jump in with some vocab. Some of this vocab, there's some space in your journal, probably around page 66. I don't have it in front of me today. So these are all in your journal. Okay. So when we're talking about domains, we kind of talked about this on Monday. Okay, we have two different types of domains that we have to be aware of and ranges that we have to be aware of. When we just have certain numbers graphed, okay, like ordered pairs, or in this case just graphs integers that are on a number line, okay, and we do not include everything that's in between our numbers here, like 1/2 or 1 1/2, 1 3/4. Okay, we just have these numbers, so in this case integers 1 to 5. This is called a discrete domain. Okay, but when we have all of them included, okay, so even our decimals and our fractions in between here, okay, that is called a continuous domain. It kind of makes sense in the word continuous. So the difference between discrete and continuous, we're going to look at kind of telling the difference between those two within story problems. Okay, and then solutions of a linear equation in two variables. So when I say that, all I'm saying is in the form y equals mx plus b. This is in two variables, y and x. So it's an ordered pair that makes the equation true. So we have an x and a y that would make this true. That is a solution of a linear equation in two variables. So these are kind of our vocab words today. We're going to use these to kind of look at a few different story problems and go from there. Okay, so here's our first one. It says, my pen has been working funny. The linear function y equals 15, well, I'll just say 15.95x represents the cost y in dollars of x tickets for a museum. It says each customer can buy a maximum of 4 tickets. Okay, so remember, x is our ticket. So if you think back to independent and dependent variables, then the cost in dollars is going to be dependent on the amount of tickets you buy. So your tickets are your independent, and your cost is your dependent. Okay, so it says find the domain of the function. So what we need to find is, okay, what can we input here for x? Okay, that's our domain because that's our independent, that's our input. Sorry, that does not look like the word independent. But that's our input value, so we need to figure out what the domain of the function is. Well, it says each customer can buy a maximum of 4 tickets. So as a customer, what are our options for how many tickets we can buy? Well, we could buy 0 tickets. We could buy 1 ticket. We could buy 2 tickets. We could buy 3 tickets. And we could buy 4 tickets. This is our domain. So, based on our definition on the previous slide here, is this a discrete domain or a continuous domain? Well, it's just these integers. It's not a continuous piece of information. And we're going to give you an example of that. But this would be considered a discrete domain because if you look back at this, it consists only certain numbers in an interval. It only has these numbers 0, 1, 2, 3, 4. Okay? So only has certain numbers in an interval. Okay, so this is discrete. And then it says graph the function using its domain. Okay, well, if we're going to graph it, we need to know, that's why we talked about on this slide, the solutions of a linear equation. We have to figure out what the y values would be here. Okay, so we can make an xy chart. So if x is 0, x is 1, 2, 3, and 4, we need to figure out what the y's would be. Well, to do that, we just plug it into the function. So in each case, we're going to plug x into whatever x we're working with, 15.95 times whatever x is. So if x is 1, well, I guess we should start with 0. If x is 0, 15.95 times 0 is 0. Okay, if x is 1, 15.95 times 1 is 15.95. If x is 2, we get 31.9 because I multiplied this by 2. If x is 3, we get 47.85. I'm realizing quickly my graph's not going to be big enough. If x is 4, we're going to get 63.8. So these are our dollars. Is this a linear function? Well, look at your XY chart. Is this a constant rate of change? As the tickets go up, is the y's constantly going up by the same? Well, each time they're going up by 15.95. So I'm going to have to make these go by 20s to make this work on this end. Okay, so 0, 0, 1, and then we'll go to 15, past 15, 2, 31, 3, and I'm just doing the best I can on this graph here, 47, sorry, I guess this would be more like right here, a little up further, there we go, 347, so like right there, and 463. So we would have this linear, this line here, but it would only be those points because we talked about it's discrete. So we wouldn't draw a line through there because we're not including everything in there. These are just the options for the tickets that we can buy. We can buy 0 tickets, it would cost us $0. We could buy 1 ticket, it would cost us $15.95. We could buy 2 tickets, it would cost us $31.90, so on and so forth. Okay, let's keep moving then. Same idea, so the linear function m equals 50 minus 90 represents the amount m in dollars of money you have after buying D DVDs. Okay, so think about quickly which one is your independent, which one's your dependent. Well, your DVDs are what you're buying, and those are your independent. The amount that you're going to spend is dependent on the DVDs. So you know that D is your input. So we need to figure out our domain, so that what can we put in? How many DVDs can we actually buy? Okay, well, we kind of have to work backwards here. So if this one's a little different because if we're trying to figure out the domain, we can't not have any money to buy the DVDs. So we cannot go negative. So we need to figure out what's the most amount of DVDs we could spend here and not be in the hole. Okay, so if we're looking at this expression, okay, if I were to plug 4 into here, say, I'd have 50 minus 36, I would still be positive, so I can go higher. If I plug 5 into here, 50 minus 45, okay, could we go higher than 5? So that's what we have to think about. 9 times 6 is 54, so 50 minus 54, we'd have negative $4. Can we do that? Well, the store won't let us do that. So now we've kind of figured out our domain. I can buy 0 DVDs. I could buy 1 DVD. I can buy 2 DVDs. I can buy 3 DVDs. I could buy 4 DVDs, and I could buy 5 DVDs. I can't buy 6 because I would run out of money. So that's our domain, which then tells us it is a discrete domain because we just have these numbers in this interval. It's not continuous. We can't buy half a DVD. That also is helpful to think about. So we could graph this. Again, you're going to plug it in. So what I want you to do on your own this time is plug this in, and then maybe on some graph paper, go ahead and graph. Plug it into the function y equals 50 minus 9d. Plug in all our x values that we've determined will work, and then graph it. And then I'll take a peek at it when you're done with that. So go ahead and raise your hand, and I'll come around and look at it while you're working on, right after you're working on this, before you move on. Okay, this is probably the last one so that the video doesn't get too long. We'll see where we're at. But it says a cereal bar contains 130 calories. The number C of calories consumed is a function of the number B of bars eaten. First question is a little different. It says, does this situation represent a linear function? Explain. So if we know that each bar contains 130 calories, and C is a function of the number of calories eaten, or sorry, bars eaten, okay, every time you eat a bar, how many calories do you have more of? 130. So would that be a function? Well, yes, because it will have a constant rate of change. Okay, so the domain of this function is pretty open-ended. It's a little different though. Okay, so remember, if we're saying that the bars eaten, the domain of this function is a little different because we can eat half a cereal bar, right? You don't have to eat the whole cereal bar. So you have a wide range of options for your domain. Your domain isn't locked into just a certain number of numbers. So actually the domain is B just has to be, the domain of this would be B is greater than or equal to 0. You could have any number because you can eat a 3/4 of a cereal bar, you can eat anything. So any number that's bigger than 0, because you're going to eat a negative cereal bar, okay, so any number that's bigger than 0 could be an option that you would plug in. So we know that for every 1 bar eaten, we have 130 calories, okay. This is a continuous graph because we're including all of those numbers. It goes from, it's not just a few different points on a graph, it's any number you would want it to be. So you can set up an XY chart. These are going to be pretty big numbers. But even if you just did 0, 1, 2, 3, and 4, okay, obviously you had 0 calories here, but if you ate 1 bar, it contains 130 calories. And you could go on and so forth. 2 bars, okay, go ahead and fill that in. And then graph it. Obviously, you're going to have to make the graphs pretty extended here, but just make them going by multiple, going by 10s or going by 50s, however you want to do it. Okay, so this one would be continuous. This one you would shade in that line. All right, we're going to look at this really quickly because we're kind of pushing time limit here, but we want to see, is this domain discrete or continuous? Okay, the inputs are what you're looking at. That's your domain. Okay, they are not a continuous thing, so the number of stories, you can't have a half a story, so that is going to be discrete. We're going to skip the last one though. If my pen will work, maybe. And I'm going to give you the homework. We may have time to go to that. We'll probably do that one over on a bell work. But your homework is on page 68 in your journal today. So you can go ahead and get started on that. Have a great day.